Hello, this is John Whitaker for the Mathematical Analysis 1 class, and this is our fourth video lecture. And today I want to start off with the concept of a field. And so it's a long definition. And here's what it says. It says, it's the definition of a field. It says a set, we call it F, with two operations. Addition and multiplication. Is called a field if it satisfies if the following uh, 11 properties are satisfied. Okay, before I write down the 11 properties, the addition is going to be denoted by a plus, and the multiplication is going to be denoted by dot, or sometimes I'll just put parentheses between elements. Okay, so here's the first property. Well, here I should say for all x, y, and z that are in F. The first property is that if you take x plus y, that is going to be F. That says that F is closed under addition. Second thing, so you take any two of them and add them together, you get something that's back in the set. If you take x plus y, that's the same thing as y plus x. That's the commutativity property. 3, we have the associativity property. What it says is if you take x plus y and then add z to it, that's the same thing as x plus the quantity y plus z. So again, this one is commutativity. This is associativity. So those are the first two field properties, first three field properties. The next one is that F contains the zero, an element, 0, such that 0 plus x equals to x, and that's for all x elements of F. This is the additive existence of the additive identity. There's some element out there that if you add it to any element in the field, you get back that any element of the field. Fifthly, is that F, it's I should say, for all x in F, there exists a minus x element of F, such that x plus minus x equals to 0. And this is known as the existence of the additive inverse. So those first 5 properties have to do with addition. The next thing we're going to look at is some properties having to do with multiplication, and they're similar to what we wrote up for addition. The first is that x times y will be an element of the field, meaning that the field is closed under multiplication. Then the commutativity part for multiplication, x times y is equal to y times x. The next property has to do with associativity for multiplication. And so that says that x times y times z is equal to x times the quantity y times z. Ninthly, f contains an element, we usually denote by 1, such that 1 times x is equal to x, and that's true for all x elements of the field. This is the multiplicative identity. 10thly, this is true for all x's in F, with x being different from 0, then there exists a 1 over x in F such that x times 1 over x is equal to 1, and this is the multiplicative inverse, and which exists for everything except for the 0 element, which is the additive identity. And 11 is the distributive property, and that is that you have x times y plus z. That's equal to xy plus x z. Again, this is the distributive property. So that's what it takes to be a field. It's a set that has these two operations that satisfy these 11 properties. Well, let's look at some examples. And then we're going to look at some properties of fields. So as examples, it turns out that Q is a field. And then the set of natural numbers is not a field. And one of the reasons it's not is that 3 is an element of the natural numbers, but the additive inverse of 3 is not in the set of natural numbers. Also, I want to give some definitions here, or some notations. Is that we can have x minus y, which is really defined by x plus minus y, where minus y is the additive inverse of y. So this is the way that we're defining subtraction. Okay? And so really we only, for a field, we have addition and multiplication. So I could say, well, here's what x minus y is. It's x plus, because we know what plus is, the additive inverse of y. Similarly, we can define division as x over y is equal to x times 1 over y, and that's for y being different from 0. Okay? And so what we do is we're defining division, x divided by y in the field, by a multiplication, x times 1 over y, where 1 over y is the multiplicative inverse of y, and that exists for every y that isn't 0. And we don't define division by 0. Okay, now on to some properties. Good many properties about fields. So here's a proposition. This is a small mathematical fact. That's what this word's used for. It says, let F be a field, and X, Y, and Z be elements of F. Then, really, this proposition will have three things. The first claim that we're going to have is if X plus Y is equal to X plus Z, then Y equals to Z. 2, if X plus Y equals to X, then that means that Y had to be equal to 0. 3, if X plus Y equals to 0, then that says that Y equals to minus X. A fourth property is minus a minus X is the same thing as X. So we want to prove these, and we're just basically going to be able to prove the first part from the field axioms. Okay. So here, this is the proof. This is for 1. We're going to let X plus Y equal to X plus Z. We want to show, excuse me, that Y equals to Z in this case. And so the way we're going to do this is we're going to start off with Y, and what we're going to say is, well, Y is the same thing as 0 plus Y. So 0 plus anything is the anything. And then we're going to rewrite 0 as X plus minus X plus Y. We're going to commute these, and we're going to get minus X plus Y. Then we're going to do association to say this is the same thing as minus X plus the quantity X plus Y. And then we know X plus Y is the same thing as X plus Z, so we make that substitution. So it's minus X plus Z. We reassociate the x's type terms together. So it's minus X plus Z. And then, well, I'll recommute these to get X plus minus X plus Z. But the X plus minus X is 0. Plus Z, and 0 plus Z is just Z. So we have shown that Y equals to Z. And we're just using the field axioms there. Okay. I was really careful in that proof to follow all the steps. Eventually we'll get to the point where we will skip over steps there. But right now, just be very careful. So the second, what we want to do is we're going to let x plus y equal to x. We want to show that y equals 0. And so here's what we have. Since x plus y equals to x, then we have that x plus y equals to x plus 0. Now, from the previous fact, if we got x plus y is equal to x plus z, that means that y has to be equal to z. So from part 1 of this proposition, y has to equal to 0. And that's what we wanted to show. So that ends that. The third property that we want to show, if you'll remember, was if we're going to let x plus y equal to 0, what we want to show is that y equals to minus x. And the way we're going to show that is using part 1 again. So since x plus y equals to 0, then we have that x plus y is equal to x plus minus x. And again, from part 1, if you have x plus y is equal to x plus z, then y has to equal to z. So here, by part 1, y has to be equal to minus x. And that ends that proof. Okay. So the next thing we want to do is the fourth property, and that is we're going to let, or we want to show that minus a minus x equals to x. Okay. And so the way that we're going to do this is use the part 3. So here, note that x plus minus x equals to 0. So what did part 3 say? Part 3 would say if you have a first guy plus a second guy equal to 0, then the second guy had to equal to minus the first, add to the inverse of the first. Well, here, that would just say if we apply part 3 directly now, we have minus x is equal to minus x. That's not very substantial, and it's not what we wanted to show. So what we do is that we commute these, and so what we have is minus x is, plus x equals to 0. Now applying the third part of this property, we have x, so by part 3 of this proposition, we have x is equal to, it's minus this quantity, so it's minus a minus x. And that's what we were trying to show. So that ends that. Okay. The next thing that I want to do is look at another proposition. It's got 4 parts. And it has to do with multiplication. So it says, let x, y, and z be in F, where F is a field, then 1, if x x is different from 0, not equal to 0, and x times y equals to x times z, then what we have is that y has to equal to z. 2. Again, if x is different than 0 and x times y equals to x, then y had to be 1. Thirdly, if x is different from 0 and x times y equals to 1, then y equals to 1 over x. And lastly, I'm going to squeeze this part 4 in here. It says, if x is different than 0, then 1 over x is the same thing as x. Okay. So, how do we prove this? Well, it's the proof. We start off with part 1, and so we let, in all our problems, let's have this precedence. Let's let x be different from 0, because all of our parts have x being different from 0. Okay, then for part 1, what we'll say to prove it is we let xy equal to xz. We want to show that y equals to z. Okay, well, we'll start off with one side. We'll look at y. So note, y is equal to, well, it's equal to 1 times y. And now, what I want to do is I want to get x times y involved. Okay? So I've got y is equal to 1 times y. And so I'll rewrite 1 as x times 1 over x times y. And then we'll commute the multiplication here. And we'll have 1 over x times x times y. Then we'll reassociate at 1 over x times y. That's what we are. But I can substitute in for x times y what it's equal to, which is x times z. So 1 over x times z. Reassociate to get 1 over x times x, all that times z. And then commute to get x times 1 over x times z, but that's equal to 1 times z, which equals to z. And so we have y equals to z, and that's what we want to prove. Again, here I was being very careful with all the details. For part 2, so here for part 2, we're going to let x times y equals to x, and we want to show that y has to be equal to 1. Okay. Well, since x times y equals to x, then x times y equals to x times 1. And so by part 1, we're in this situation y, our conclusion for part 1 is that y, x times y is equal to x times z. That means that y has to be equal to z. So by part 1 of this proposition, y has to be equal to 1. Okay. Okay. Next thing we're going to do is prove part 3. And so for part 3, what we had was we're going to let x times y equal to 1. We want to show that y equals to 1 over x. Again, this is going to use part 1. So since x times y equals to 1, we have x times y equals to x times 1 over x. So by part 1, y has to be equal to this again. X times y is equal to x times z. So that means that y has to be equal to 1 over x. And that's what we wanted to show. Like that. Very simple. And then fourthly, what we want to show that 1 over x equals to x. Okay. So here we note, since x is different than 0, we have that x times 1 over x, the existence of 1 over x is there in the field. That's equal to 1. So again, what we're going to do is use this part 3, but we need to put ourselves in a great position to use it. So I will commute these two elements to say 1 over x times x equals to 1. Thus, by part 3 of this proposition. So what's part 3? It says if you have a first times a second equals 1, a first times a second equals 1, then the second is equal to 1 over the first. So the second here is equal to 1 over the first, which is 1 over x. And that is the proof. Well, we've got another proposition. Okay, here it is. It says let x, y, and z be elements of F, where F is a field. Then have the following 4 facts. 0 times x, 0 is additive, that's going to be equal to 0. 2, if x is different from 0, and y is different from 0, then x times y is going to be different from 0. 3, minus x times y will be equal to minus the quantity xy, which is equal to x times minus y. Fourthly, minus x times minus y is equal to x times y. So we want to prove these. Okay. So here's the proof. We want to do part one. So here, what we'll do is we'll start off with note. We're trying to show that 0 times x equals 0. So note 0x plus 0x is equal to 0 plus 0 times x. That's the distributive property in works here. Which equals to 0 times x. So that's the left-hand side. So 0 times x plus 0 times x is equal to 0 times x plus 0. Wait just a second. Okay. Yes, and so here's how we're thinking about this. 0 times x plus 0 times x is equal to 0x. So that part we've established here. And then we're just adding 0 to this because this is 0 times x. Okay? 0 times x is 0 times x plus 0. And so, by the first proposition, we've got one thing plus another thing equal to the same first thing plus z, if you will. So x plus y is equal to x plus z. This says that 0 times x is equal to 0. This is, as I said, this is by the first proposition that we did about the field, part one. Okay, this was the proof for part one. Here's the proof for part two. We're going to let x be different from 0 and y be different from 0. We want to show that x times y is different from 0, but we're going to do this by a contradiction. We're going to suppose x times y equals to 0. Then, what we have is that 1 can be written down as, well, I'll write it down this way. It'll give me 1 over x times x, that's 1, times 1 over y times y. And again, we get to write down 1 over x, and we get to write down 1 over y, because x and y are both non-zero. Okay, and this is equal to 1 over x times 1 over y times y. Using distributive properties, we can get something to this sort, which equals to 1 over x times 1 over y times x times y. And then we'll reassociate so that's equal to 1 over x times 1 over y times x times y. So what we have here is that 1 is equal to this 1 over x times 1 over y times x times y. Okay. Now we're assuming x times y, in this case, equals to 0. So we have 1 is equal to 1 over x times 1 over y, that's some guy in our field, some element in our field, times 0. But we know something times 0 is 0. So this says, so 1 equals to 0. But that's a contradiction, as 1 is not 0. Okay. Okay. The third fact that we want to show was we wanted to show let me conclude this a little better than what I have. So 1, since as 1 is not 0, then what happens then is so what we assume must be wrong. So x times y can't be 0. That's what I'll conclude. So remember, this was approved by contradiction. Okay, the third thing is we want to show that minus x times y is equal to minus the quantity x times y, which equals to x times minus y. That's what we want to show. Okay. So note that minus x times y plus x times y is going to be equal to, you factor y, so it's minus x plus x times y, and that's equal to 0 times y, which equals to 0. Okay, so what we have here, and I'll write this down, but let me point to it just for a second. Minus x times y plus x times y is going to equal to 0. That's what I'm going to conclude out of this. Sorry. Okay. So by previous part of a proposition, if you've got x plus y equals 0, that means that this y, the secondary guy, had to be equal to minus this. But I'll rewrite that. First, I'll say, thus, let's rewrite this, that x times y plus minus x times y equals to 0 by commutativity. And so here's what I'll say. That says that minus x times y equals to minus this quantity by, this was by property, by the third part of a previous problem, our first problem. And that gives us the conclusion we want. Okay. So essentially what we're looking at is first thing plus second thing equals to 0. That means the second thing was equal to minus the first. And I'm sorry, it doesn't conclude this part. It includes part of this part. All right. Also, to get the second part, x times minus y, x times minus y, plus x times y is equal to, I can factor out an x, and we have minus y plus y, which equals to x times 0, which equals to 0. Okay. So that says that x times minus y plus x times y equals to 0. So that says that x times y plus x times minus y equals to 0. And thus, that says that x times minus y is equal to minus the quantity xy. And so what we have then is that minus x times y equals to minus x y, which is equal to x times minus y. And that is the statement that we wanted to show. And it shows those three things that are involved in the statement are equal to each other. That's what we want to show. So that's okay. So we still have one more part to show. So for part 4, we want to show that minus x times minus y is equal to x times y. Well, here, note, minus x times minus y is equal to minus x times minus y. Okay, that's by the previous fact. Which is equal to minus x times y which is equal to x times y, and this is by part 3 of this proposition, and the fourth part of the first proposition. Okay, and that proves it. Let's take a second and look back over what's written here. So, part 3 of this proposition said that if you take minus x times the second quantity, that's equal to minus x times the second quantity. Okay, okay, and that's what we have. And then we have x times minus y is equal to minus x times y. Again, that's by that's part of that third part of this proposition. Now if we go back and look at the fourth part of the first proposition, what we have is it was minus a field element is just equal to the field element. So that's why this is true. Okay, the next thing that I want to do is give a definition of an ordered field. So here's the definition. It says, an ordered field is a field F, okay, which is also an ordered set that has an order on it, such that, but not only is an ordered field a field that has an order, that's an ordered set, it also satisfies two things. It's such that for all x, y, and z elements of F, the first thing is if x is less than, if y is less than z, then x plus y is less than x plus z. So if you add two things to the order, it still maintains the order. Add the same thing. And then part two, if x is greater than 0 and y is greater than 0, then x times y is greater than 0. And just a comment about that, if x is greater than 0, we say x is positive. Likewise, if x is less than 0, we say x is negative, just as we would normally. So an ordered field, again, is a field that is an ordered set and satisfies two things. One is if you have a relation y is less than z and you add the same thing to both sides, it still maintains that relation. And if you take two guys that are bigger than 0 in the field, when you multiply them together, you get something that's bigger than 0. Let us list an example here. So we'll end with just an example. So as an example, the set of rational numbers with, is an ordered field with our normal definition. Less than. Okay, that's enough for this lecture.